Okay, tonight we're going to be looking at magnetics, and we've got some example problems and then a wrap-up discussion. This is the last topic in the DC series. Can everybody hear me okay, and can everybody see my screen?
Looks good.
I can hear you and see you fine.
Okay. Well, that
can hear you loud and clear, Ken.
Okay, good. Okay, magnetics and inductance. As we finished up last week, we were talking about what sequence we cover those topics, and I've done it both ways. Sometimes I always do capacitance first, and then it's either inductance and then magnetics, or sometimes magnetics and then inductance. They go so hand in hand. In fact, some of the older edition textbooks, it was all in one chapter anyway. But we'll finish up with magnetics tonight. And this is just a little bit of a review here. Flux density, and of course, as we said last week, anytime you have a magnet, it has a north and a south pole, and it has lines of magnetic flux. And we can think of that a little bit like current, the flow of electrons through a conductor. This is magnetic lines of flux that flows. The flux density is equal to the flux in Webers divided by the area in square meter. The unit of measure is Webers per square meter, or Tesla, only referred to as Tesla. And in the case of an electromagnetic system, you have a magnemotive force is equal to the number of turns of wire on the coil times the current through the wire. And it's measured in ampere turns. Remember back when we were in elementary school and we played with electromagnets, and we'd take a flashlight battery and a nail and a coil, a little piece of wire, make a coil around the nail, and then we could pick up paper clips with it. So we made our own electromagnets. Now, let's compare that with electrical terms. The effect is equal to the cause divided by the opposition. And as long as the cause is greater than the opposition, then the effect will be a net positive effect. Now, in electrical, what we're trying to obtain is current flow, the flow of electrons through the conductor. And what causes that is the voltage, or electromotive force, and what's opposing that is the resistance. So I is equal to V over R, and we all know that as Ohm's law. Well, in magnetic circuits, what we're trying to accomplish is magnetic flux. What's causing it, the force, is ampere turns, and what's resisting it or opposing it is the reluctance. And that reluctance depends on what material we have the core of the magnet made up of. Some materials have better magnetic properties than others. Okay, flux is equal to the force divided by the reluctance. The force is equal to the number of turns times the current. Now, magnetizing force, now we're looking at magnetics. Magnetizing force is equal to the magnemotive force divided by the length of the core. So H is equal to Ni over L, because the force is equal to number of turns times the current, and of course the length, we're talking about the length of the core of the electromagnet. Flux density is equal to the permeability times the magnetizing force, which is represented with H. Permeability, again, depending on the material that the core is made out of. Typically, they're made out of sheet steel, cast steel, something similar to that. Okay, now I've got a couple of example problems here. We're to find the flux density, and we're given that the flux is 4 times 10 to the negative 4th Webers, and the area is 0.01 square meters. So the density is equal to the flux divided by the area. So we divide those, and we come up with 0.04 Tesla. That would be 0.04 Tesla. That is your flux density. Okay, the next one. These are what I refer to as one-liner type problems. Here we're going to find the reluctance, and we know the flux is 4.2 times 10 to the negative 4th Webers, and we know that our magnetomotive force is 400 ampere turns. So the reluctance, which is kind of like resistance electrically, is equal to the force, which is kind of like voltage electrically, divided by the flux, which is kind of like current electrically. So we got 400 ampere turns divided by 4.2 times 10 to the negative 4th Webers, and that's about 952 times 10 to the 3rd ampere turns per Weber. Okay, now on this next one, we've actually got a pictorial representation of an electromagnet. We've got a donut-shaped core made out of cast steel. The cross-sectional area of that core is 0.009 square meters. The radius of that donut is 0.08 meters. And the current is 2 amps. And we have 100 turns on our coil. It's made out of cast steel. Now, I've indicated BH curves here. BH curves, as long as we know B, we can find H, or if we know H, we can find B simply by looking at a set of curves and looking at the curve for cast steel core. There are also sheet steel and cast iron and so on and so forth. Now, most textbooks would have a set of BH curves in it in the section on magnetics. I did not make a copy of BH curves. I'll just give you that information as we go along with these problems. So what I need to know is the length of the core. Well, since it's a donut shape, we're talking about the length around the circle, so that would be the circumference. To find circumference, it's pi times the diameter, so 3.14 times 2 times 0.08. Okay, the 0.08 is my radius, so the times 2 times the radius would be the diameter, and that is equal to 0.5 meters. So the length around is 0.5 meters. Now, the number of turns times the current is equal to H times the length. So let's plug in what we know. 100 turns times 2 amps is equal to H times 0.5 meters. So that would be 200 divided by 0.5 is 400 ampere turns per meter. That is H. Okay, now remember what H is. Go back. H is your magnetizing force. Now, from the BH curve for cast steel, H being 400 ampere turns, if I look at that curve, I would see B, which is my flux density, which would be 0.68 Teslas. Now, my flux is equal to the flux density times the area. 0.68 Tesla times 0.02 or 0.009 square meters gives me about 6.12 milliWeber. Would be my flux. Okay. Any questions or comments on this introduction to magnetic circuits?
Makes sense so far, Ken.
Okay. Okay, now on our next slide, we've got another problem. This time we have a series circuit. We have two coils on a similar donut-shaped port. N1 is 2 amps, or I1 is 2 amps. N1 is what we're looking for. We don't know how many turns is on that coil. On the second coil, we've got 1 amp, 30 turns, cast steel. The length I give you is 0.2 meters, and the area is 0.0012 square meters. We're to determine N1. Now, as I mentioned last week, we're going to try something a little bit different. We're actually going to work these problems out as we go along, rather than having them worked out ahead of time. So, if you want to get you some scratch paper and something to write with, and maybe a calculator, let's work through these problems. Okay, are we ready? Everybody out there ready?
I'm still setting on my computer, but you can get started and I'll catch up.
Okay.
I'm ready.
Okay. Okay, we know that N times I is equal to H times L. So in this case, we'd have N1 times I1 plus N2 times I2 is equal to H times L. Okay? We also know that the flux density is equal to the flux divided by the area. Now, if we look at the flux, we've got 12 times 10 to the negative 4th Webers divided by 12 times 10 to the negative 4 square meters. That would give me 1 Tesla. Okay, now from the BH curve, 1 Tesla for the density is equal to 750 ampere turns for the magnetizing force, H. Okay, so N1 times 2 amps plus 30 times 1 amp would actually be equal to 750 ampere turns times 0.2 meters. So N1 times 2 amps plus 30 is equal to 150. So N1 times 2 amps is equal to 150 minus 30, or 120. So then N1 would be 120 divided by 2 amps, which is 60 turns. Now, if you'll notice on this problem, we left off a little bit of the information. Probably caught it as I first started. The area we have, the flux, is what I left off. The flux is 12 times 10 to the negative 4th Weber, so that should be written on the problem as a given piece of data. Sorry about that. So make that notation on that problem. That the flux is equal to 12 times 10 to the negative 4th Weber, as it was on our previous problem. Okay, questions on that one? Everybody ready to go on?
You might have seen I'm online, so I'm good to go.
Okay. Everybody okay with this past problem? Okay. Now we're going to kind of switch gears a little bit, and we're going to look at the types of problems that you would see at the college level on perhaps a final exam for DC circuits. We're looking at series parallel networks involving not only resistors but also inductors and capacitors. Now this next slide, I don't know what is wrong with my scanner, but you can put a stack of papers in it, and I'll guarantee you every time there's at least one that has to go through crooked. The rest of them will go through straight, and it's not the same one that gets crooked every time. So I'm not sure just what's going on here. But this one slid a little bit, and the voltage source is 50 volts. You need to know that. It's 50 volts. Now, it says 10 time constants has passed. So what do we know about the capacitors and the inductors? Well, since to fully charge a cap requires 5 time constants, and we've already passed that, we know that the capacitor is fully charged and it acts as an open circuit for DC. An inductor, after the 5 time constants has passed, we know that it acts as a short for a piece of wire. So everywhere we see an inductor, when I analyze a circuit like this, and I know that my time has elapsed to where I'm at a steady state condition, everywhere there's an inductor, I just take and draw in a piece of wire. Just a straight line. Okay? So those are the same as a piece of wire. And then I make a note everywhere there's a cap, and I just put open circuit. Now, what we want to know on this particular circuit is what is the voltage for C1, what is the current through L1, what is the current through R5, which is that 6 ohm one way out there on the end, and what is the energy stored by the cap. Okay. as typical, we need to find our total resistance of our network to begin with, so we can find current and then divide these currents up. When I look at the total resistance of this circuit, I start to furthest point from the supply, and I have R5, which is 6 ohms, is in parallel with R4, which is 3 ohms. And L2 just acts as a piece of wire, so that's not going to affect my resistance any. So I've got 3 in parallel with 6. That would be 18. 3 times 6 is 18, divided by 3 plus 6 is 9. That would be 2 ohms. That 2 ohms is in series with R3, which is 3 ohms. So 2 plus 3 is 5 ohms. Okay, now what about R2? Well, since C1 is an open circuit, analytically, R2 would not be in the loop because there's no current path through it. There's no current that can go through C1 once it's fully charged, so therefore there's no current through R2. If there's no current through it, then there'll be no voltage drop across it, so analytically we can take it out of the circuit. And what I normally do in analyzing one of these is I would actually put a X over R2, and I generally do it as a dash line because I know that that's just for analytical purposes. So then we're up to R1, which is in series with all that we had before, and when we left off we had 5 ohms. Now we've got 20 in series with that, would make 25 ohms. So my total resistance is 25 ohms. Then my total current would be my source voltage, which is 50 volts, divided by my total resistance of 25 ohms. I believe that would be 2 amps. Okay, does everybody agree with me so far?
Absolutely.
Okay. So now let's look at the voltage for R1. Voltage for R1 would be, as a series resistor, would be 2 amps times 20 ohms. That'd be 40 volts. Okay, so how much would be left for the voltage across C1? C1 would be my source voltage minus R1, which is 50 minus 40, or 10 volts. So we would have a potential difference of 10 volts across C1. Now the current L1, if we look at that loop, our main loop goes from R1 through R3, okay, and then we have a junction, part of it going through R4, part of it going through R5, joins back together, and flows through L1. And L1 acts as a piece of wire once our time constant is past 5, and we're at 10. So the resistance would be 0. So we have our total current, which was 2 amps, would be the current for L1 at that time. Okay, now we want to know the current for R5. Okay, what we need to do is look at the junction. That junction, which is right above R4. We've got our source current coming into that junction, which was 2 amps. Using the current divider rule, we've got a resistance through R4 of 3 ohms and a resistance out through the rest of the branch of 6 ohms. So to find the current through R5, we put the resistance of the one we're not really looking for, so that would be 3 ohm, divided by that 3 ohm plus the resistance of the other branch, which is 6 ohm. So that's 3 over 9 times the current coming into the junction, which was 2 amps. That gives me 0.66 amps. So that would be the current through R5. And then the energy stored by the cap is equal to 1/2 times the capacitance value times the voltage across the cap squared. So that would be 1/2 times 6 microfarad times 10 volts squared. 10 squared is 100 times 6 is 600 times 1/2 is 300, and it would be microjoules. 300 microjoules. Now, if you'll notice the way this problem is written, we could do this at less than 5 time constants. We could figure out what's 3 time constants, or a half of a time constant, whatever time we wanted to put on there. And to do that, we would simply just add a switch, and we would say the switch has been closed for so many seconds, or so many milliseconds, whatever. Which means, if you recall, they would have to go back and find what the time constant is, whether we're charging the cap or the inductor, whichever one we're asking for. They'd have to figure out what the time constant is, and then they would have to figure out tau, and then they would have to use the exponential functions to find the voltages and currents at that particular instance in time. So a problem like this, there's lots and lots of possibilities of the questions that you could ask from a simple circuit like this. One of the common mistakes that occurs with calculating the energy stored by the cap, students tend to put in source voltage there rather than the voltage across that particular cap that is involved. Okay, questions, comments about this particular problem?
Could you clarify time constant?
Okay, the time constant, if you recall from when we were talking about capacitance, is the resistance in the loop times the capacitance value. That's the length of a time constant, and it charges as an exponential function, which is like 63.2% in the first time constant, and it keeps going up exponentially. And after 5 time constants, it's 99.99% charged, so we consider it to be fully charged. And then for an inductor, it's L over R, and a capacitor, it's R times C. That's how you find the time constants. Now, if it's in a loop and there's more than one resistor, then it's your total resistance and your total capacitance.
Okay.
Okay? Okay. Now let's look at another circuit. A little bit bigger. This one, I put the circuit has been energized for a long time. With that, we would assume a long time means more than 5 time constants, because time constants is usually going to be measured in seconds or milliseconds. So We are looking at it at a steady state condition. The caps are fully charged. The inductors are now acting as a short. The capacitors are now acting as an open circuit. So we got 50 volts. C2 is tracking parallel across the 50 volts. It's 10 microfarads. Then we've got R1 is 5K, R2 is 1K. Then in the next junction there, we've got C1 is 5 microfarads, R3 is 5K. Then we've got L1 in series, and then we've got a 10K in parallel with a 6 Henry inductor. Then we have R5 being 4K. Well, first of all, C2 is acting as an open circuit, so I would write the word open on that one. C1 is also an open. So if C1 is open, no current going through it, that means there's no current through R3. If there's no current through R3, then there's no voltage drop across R3, so analytically wouldn't be included in the circuit. Now, L1 acts as a short piece of wire, so no problem there. Zero resistance because it has a long time has elapsed. Then we've got 10K R4 in parallel with L2. Well, after the 5 time constants, L2 acts as a shorter piece of wire. So that 10K has a piece of wire strapped around it. So it is shorted out. So therefore there'd be zero resistance through L2, so 10K can be analytically removed from the circuit as well. Now, R5 with 4K is now in series, in that series loop. So if we look at our current loop from the voltage source, we would have source current going out to that first junction. Part of the current going through R1, we call that I1, and the rest of it going through R2, and which is in series with, go right through the inductor, the 2 inductors right around, and you've got R5 in series with it. So you have R2, which is 1K, and R5, which is 4K in series, so add them, that's 5K. And that 5K would be in parallel with R1, which is 5K. That's our current loop. That's the total resistance. 5K in parallel with 5K, which gives me 2K. Or excuse me, 2.5K. So my total resistance of my circuit is 2.5K. So my source current would be my source voltage of 50 volts divided by the total resistance of 2.5K, 20 milliamps. Okay, now let's go to that first junction and use the current divider rule. We've got 20 milliamps coming into the first junction. R1, which would be I1. We've got 5K of resistance going that direction. Now, if I look going the other direction, I've still got 5K going around the rest of it, so it's just going to divide evenly. So I would have 10 milliamps for IR1, and that's one of the answers that we were asked trying to determine. So the current for R1 is 10 milliamps. Okay, now we can go out there and find the power for the source, which is the source voltage times the total current. 50 volts times 20 milliamps, that'd be 1,000 milliwatts or 1 watt. Okay, now the voltage for C2. Well, it's in parallel with our source voltage of 50 volts. And once it is fully charged, then it would be charged to that voltage level that's applied to it. So it would be 50 volts. And then we're looking for the current for R4. Well, how much current would go through R4 when it has a piece of wire strapped around it? Because that's what L2 acts like. It'd be 0. Because the current at that junction would have a choice, going through 10K or going through a resistance of 0. It's going to go through, all of it's going to go through the resistance of 0. So R4 is shorted out of the circuit by L2, which is the 6 Henry inductor. And again, that occurs after the 5 time constants. Now, during that time, there would be some resistance in L2, at which then we would have some current through R4 and some through L2 until L2 becomes 0 resistance. At that point, then all of the current goes through L2 and none of it through R4. And that's an exponential function, which would occur in just a few seconds or milliseconds, whatever our time constant figured out to be. So you can see how these types of problems bring in just about everything we've talked about. We haven't brought in mesh analysis or Thevenin's theorem at this time. Those would be problems that would be added on as standalone problems for a final exam. And then we've got Y delta and delta Y conversions, and if you've looked ahead, the next problem is going to get into that. Okay, questions, comments on this particular problem that we've worked through?
Think about my track record.
Sorry, I'm giving a little background noise here. No, this looks good.
Okay.
I think. Yeah. I was showing a couple of these to one of my best students, and he was looking at it and saying, "Yeah, I could do that. I think this simplifies out, and this comes out." And so it was another problem I was showing him, one from another week. So I think but I think there's only a couple of students that are capable at this level in my graduating class. And a lot of this is going to be stuff that they really have to kind of get on their own a little bit. I don't know how familiar you are with the Ohio Department of Education standards, Ken, for high school.
Fairly.
Okay, because that's a thing that I'm noticing is, at least from a non-electrical engineering background, I see a lot of depth in content. Some 60 line items of electrical standard or electrical topics to go through digital electronics.
Right.
So I don't know. Is there, if you're familiar with them, and I almost would wish that someone with your background could kind of review and say what's important for high school. And maybe that's been done. I'm sure it's been done, but
well, that's where
I think
the C-tags have been kind of odd with the Ohio Department of Ed, because the Ohio Department of Ed wants all of those topics in there, and the problem being that the student that goes through the program, they've got a little bit of knowledge about a lot of different things, but they don't have enough depth in any one thing. And that creates a problem in giving college credit because
That's right.
what we're doing at the college level, you have a DC course, an AC course, an electronics course, and then you have a digital course. Well, in order to get credit for the digital, all those other courses are prerequisites for digital.
That's right.
So you have to go through all of that. And you can't expect a high school student to do all of that in one course. And if we're going to pick DC, then we have to make sure that we have the depth in DC so that they are complete with the DC course.
That's right.
Equivalent to the college level. And then they could go on for the AC and so forth. And that's where the problem is with your time constraints. By the time you get all of DC in, you don't have much time to get all the rest of it in that Department of Ed wants.
And let me ask, just in your opinion, getting them, because ultimately the name of my course that I'm teaching is digital electronics, and it sounds like there's a lot of stuff that leads to digital electronics. So for them to actually to get what would be what you have as at a college level DC, not DC, digital electronics. They'd have to go through a lot of depth in a lot of areas, DC, right. AC, electronics, before they got to. I guess it would be DC and AC because you mentioned that electronics and digital can be taken at the same time. Right. I think you said that.
Right. They can be taken at the same time. And in some cases, we do AC and get them started into electronics at the same time. But when we're looking at electronics, basically we're getting into the idea of amplifiers. We start off with diode, work our way up to amplifiers, discrete components, and we put them all together in the IC chip, and we're switching into digital at that point. But to truly understand what's happening inside those chips, you need the electronics part of it. But see, we're trying to give people enough background that if they want to go into digital, they can go into digital. If they want to go into automatic control systems, which leans a little more on operational amplifiers and understanding amplifiers, which gets a little more into the electronics end of it. Or if they go into motor control, more AC. So we're preparing students to go to any of those, not just one of them. And with the Department of Ed, they seem to be trying to hone in just on digital. And
sure.
Doing that leaves a lot of the other stuff off, which means that your student coming to us is going to be lacking in those other things, so they're not going to be able to get equivalent credit at the college level.
Sure. Without some work on their part. And I mean, that's what I've told my incoming class is they earn this credit. There's a lot of work to be done even outside of this class.
Right. That's for sure.
And they've been receptive to that. Framing it that way. Now I have some high flying juniors too, so we got a little time to.
Yeah, I think that may be part of the solution to the problem. That in order to get everything in, that it's going to have to be across 2 years rather than one. Well, and of course, that's the electronics. Digital electronics is 1 out of 4 courses that I'm teaching. So while I can incorporate some of that in the other ones, I have about half a year to really cover what I need to. But typically, I apologize, guys. I gotta get going. I just looked at the time. And I got to get to my other class here for my certification, my teaching.
certification. So I'm gonna head out. But Ken, thank you as well. It's been great.
Okay.
And Rob, I'll see you another time here soon. Take care, guys.
Okay, you too. Okay, does anyone else have any questions or comments? If not, we'll take a look at this next slide. Slide number 6. Got another little problem here. Okay, now if we look at this one, we've got a 100-volt port. We have 10 microfarad cap and a 10 Henry inductor. Those two in series, and they're strapped in parallel across the voltage source. Now on this one, I did not specify at what time we're talking about. We're going to work through this with the assumption that 5 time constants has passed. This question can be written so that you specify what time that you want it to be. But in what we're going to do here, the caps are fully charged, so they're acting as open circuits. The inductors are acting as a short circuit. Okay, R1 is 10K, R2 is 10K. And down here we've got L2, which is acting as a short, like a piece of wire, is 6 Henrys. Now we go over to here and we've got a bridge network. And then strapped across the bridge, parallel with it, we've got a 5 microfarad capacitor, C2. Again, if it's fully charged, it would be acting as an open circuit. There's no current flow through it. Now, the first question we need to ask ourselves, is this a balanced bridge? Because if it is a balanced bridge, then R5 would have 0 current through it and 0 voltage dropped across it. Well, if it's a balanced bridge, then R3 over R6 would have to equal R4 over R7. So we're asking ourselves, is 3K over 1K equal to 3K over 2K? Obviously it's not. So it's not a balanced bridge. So there is current flow through R5, and there's a voltage drop across it. Now, to analyze this circuit, what we need to do is, you notice you've got a delta circuit arrangement here. You've also got a delta arrangement on the bottom. We're going to convert one of those deltas to a Y. And I chose to do the top one because, if you'll notice, 3K, 3K, and 3K. That's what we call a symmetric Y, or a symmetric delta. So we can use our shortcut method and make it into a Y. Now, when I make that into a Y, I end up with a resistor here, one here, and then together they join and they do resistor up here, making a Y connection. Okay? To convert this top delta to a Y, it is a symmetric delta. So to find what each of the resistor values in the Y connection would be, we take one of these resistor values, which is 3K, divided by the 3 resistors. 3K divided by 3 is 1K. So we would redraw the circuit as a Y. You would come down here with a 1K resistor, and over here with a 1K resistor, and then from the center over to here with a 1K resistor. Putting a Y up here, just like we did a couple sessions ago when we were talking about Y to delta conversion. So all 3 of those would have 1K. Now, with that, R5 disappeared. Okay, now let's find our total resistance. Right here, you've got 1K. You've got 1K here. Then you're going to come down with 1K and then 2K. Okay? You have 1K, and over here with 1K, down here with 1K. Well, let's look the top 1K is in series with the rest of those. So you've got 1K in series with 2K, that group in parallel with 1K in series with 1K. So 1 plus 1 is 2, and over here you have 1 plus 2 is 3. So you've got 2K in parallel with 3K. 2 times 3 is 6, divided by 2 plus 3 is 5. That's 1.2K, plus the 1K, which is this top resistor that is in our Y connection now. That's 2.2K. So all of that network now, that whole grid circuit becomes 2.2K. That 2.2K is in parallel with 10K. So that would be 2.2 divided by 12.2, which is 1.8K. All that 1.8K is in series with the 10K, which gives me 11.8K. So my total resistance is 11.8K ohms. Now I can find my total current is my source voltage divided by my total resistance, 100 volts divided by 11.8K, and here I did just a little bit of rounding. It's 8.5 milliamps. We get 8.5 milliamps. Okay, we are looking for the current through R2, that's this 10K. The voltage across C2, that's the voltage way out here. The current through L1, that's the current over here. And the current through L2, that's right here. And the energy stored by C1, which is over here. Well, I'm going to use the current divider rule, and I'm going to go to this first junction right here. Coming into that junction, I would have my total current, which is 8.5 milliamps. In this direction, for I2, looking at that leg, I've got 10K of resistance. My resistance back this direction was 2.2K. So to find I2, we put the 2.2K on top, divided by 2.2K plus the 10K, times 8.5 milliamps. And I come up with, again, about 1.5 milliamps. So I, for R2, which is one of the things we're looking for, would be 1.5 milliamps. Now the voltage for C2. Well, the voltage for C2 is in parallel with R2. Okay, we can find the voltage for R2, which is the current through it, which we just found, 1.5 milliamps times 10K, 15 volts. So if there's 15 volts from here to here, then there's 15 volts across C2. We can check ourselves. Let's find the voltage for R1. Okay, that's the total current of 8.5 milliamps times 10K, that's 85 volts. We started with 100 volts. Going around our loop right here, we've got two resistors in series. R1, 85, R2, 15. That's 100. That's all of our voltage. So we just check ourselves to make sure that we are correct. So R2, which is the same as C2 voltage level, is 15 volts. Now the current through L1. Well, if we look at this loop over here, once that cap's fully charged, no current can flow through it. Therefore, it's an open circuit. So how much current is through L1? 0. Okay, now the current through L2. Well, the current through L2, this would be back, you've got total or source current going this direction. It divides part of it here, part of it down through here, combines back here, and we have, at this point, total current again, which in this case is 8.5 milliamps. Then we're looking for the energy stored by C1. The energy stored by C1 is equal to 1/2 times the capacitance value of C1 times the voltage across C1 squared. 1/2 times 5 times 15 squared. I come up with that being 562.5, and it would be microjoules because we got microfarads. Okay, questions about this particular problem?
I was just curious about that circuit. You mentioned that another circuit was a temperature sensing type circuit. Does this circuit have a purpose, or is it just a good instructional tool?
Well, what was mentioned earlier is you could use this in a temperature sensing circuit, but to do that, one of these resistors would have to be a thermistor. Okay, in this case, it's just a resistor. I just put them in as resistors. That was just one application for that.
Okay.
Okay.
This is a little bit of a different question, maybe more of a general question, but one of the things that I've noticed is, well, like in Ohm's law, even when you use Ohm's law, the units don't come out.
Okay, you seem to be cutting out on me here.
Is that better?
Yeah, that's much better.
Okay. Like the units, a lot of times the units will not work out. Like, you know, if you're doing miles per hour or whatever, you can cancel units, but a lot of times the units don't cancel.
Well, the units here, remember K is times 10 to the third, and micro is times 10 to the negative 6 in this case. Milli is negative third. They should cancel out with the exception of whenever we start talking Henrys and farads, because those actual units are named after the physicists that developed these concepts and did research with inductors and capacitors. That's how they got those names. But aside from that, the units should cancel each other out.
Okay.
Not quite as readily as miles per hour and feet per second and so forth. I agree with that. Okay, anything else? Okay, this next one, as you see, is a blank screen. So I do have one more problem. And this one, I just want you to draw out the circuit as we're going along. We've got a 25 volt, it's a DC 25 volt source. In series with that source, we've got a 2 Henry coil. We've got a 2 microfarad capacitor. This is all in series. Then we have a 3 microfarad cap. Then we have a 100 ohm resistor. And then back to our supply. "25-volt source, 4 elements in series, which is a 2 Henry inductor, 2 microfarad cap, 3 microfarad cap, 100 ohm resistor. Just one series loop." Okay, have you got that?
Yes.
Okay. Now, here's the question. I want to know what is the voltage. Now, we're talking about steady state voltage. This is after the charging cycle, after the 5 time constants and all that. We want to know the voltage level for C1 and for C2. So that would be the voltage across each of the 2 caps. Okay, now if we look at this loop, after they're fully charged, there's no current flow through that loop because the caps acts as open circuits. Okay, the inductor acts as a short circuit, so that's the same as piece of wire, so there's no resistance there. And you've got a 100 ohm resistor in series, but once those caps are fully charged, it's like an open switch. So all of my voltage has to be dropped across the 2 caps. Okay, so I know that we're going to drop 25 volts across those 2 caps together. But what I want to know is what's the voltage level across each of the individual caps. Now this one gets a little trickier. So what we need to do is find our total capacitance. Total capacitance would be C1 in series with C2. Now remember, caps in series, it's product over sum. You treat them just the way you would resistors if they're in parallel. So you've got 2 microfarads times 3 microfarads divided by 2 plus 3. So 2 times 3 is 6, divided by 5. Okay, 6 divided by 5 is 1.2 be microfarads. That's my total capacitance. Okay, we all right to that point?
Yes.
Okay. Now, to find the voltage across the cap, either one of them, so I'm going to say the voltage for C1 is equal to the charge, Q of C1, divided by the value of C1. Okay, and we do the same thing for C2. It would be the charge for C2 over the value of C2. Now the problem is, what's my charge? We don't know that. Okay, Q for C1 is equal to Q for C2 because they're in series. And to find the charge, it is your total capacitance times the voltage, the maximum voltage that would be across there. Okay, so CT times the maximum voltage across the two of them together is 25 volts. So that'd be 1.2 microfarads times 25 volts. That's 30 micro. Now the units for charge is coulombs, which we talked about that a couple sessions ago when we were in capacitance. Or maybe it was last session, I don't remember now. So our charge is 30 microcoulombs. So if I look for the voltage for C1, would be the charge of C1, which is 30 microcoulombs, divided by the value of C1, which is the 2 microfarads, and that gives me 15, and it's going to be volts. Now the voltage for C2 would be the charge for C2, which is 30 microcoulombs as well, divided by the value of C2, which is 3 microfarads. That's 10 volts. Now if I look at those two voltages, 15 plus 10 is 25 volts. Just like if those had been resistors, the sum of the individual voltage drops around the closed loop has to equal the applied voltage. That's the law for a series circuit. Well, let's look at this. We have L1, which after the time has elapsed and everything's fully charged, we're at steady state condition, it acts as a short, a piece of wire. So it has zero resistance. Okay, now we just found that the voltage for C1 is 15 volts, and the voltage for C2 is 10 volts. That's my 25. So what's my voltage for R1? Well, my voltage for R1 has to be 0. There's not any left.
Right.
Well, how do we find the voltage for R1? Would we not take the current through R1 times R1? Well, we know R1's 100 ohms, so it'd be small voltage to begin with, but how much current is going through R1 once the caps are fully charged? Remember, once they're fully charged, they act as an open circuit. There's no current flow. So since there's no current flow through R1, it'd have to be 0 volts. So mathematically, it all adds up too. It's not just, spouting out a bunch of rules, but we can prove all this stuff mathematically. And I use this particular little circuit to verify that the laws of series and parallel circuits holds true whether we're talking purely resistive or whether we're talking about inductive and capacitive as well. Okay, any questions on this? Okay, who we have left? We've got 2 or 3 still on the line here. My intent was to be able to spend the last half hour or so discussing the concept of the C tags and what's expected of the college level of the student coming to us from these career tech centers, and you as instructors in these programs at the career tech centers, what problems you are anticipating, what you're currently having, concerns that you have. Be candid. Is this type of little workshop that we put together, is it beneficial to you? Again, we're not trying to teach the course. We're not trying to come across that, well, we know how to do this and you don't, because, you wouldn't be an instructor there if you didn't know how to do all this stuff. It's just a matter of giving you kind of a snapshot glimpse of the depth that we are trying to achieve at the college level, and for your student to get that same college credit, they have to achieve that same depth. And again, you know, I only showed 2 or 3 example problems of each thing. You know, we spend quite a bit of time lecturing, discussion, doing labs, hands-on, so that they can see these concepts. And then these are just example problems that would be on an exam or so forth to verify that they do know how to do this. So they should be able to do this without intervention from anybody leading them through, that they can think their way through these types of problems. So I'm going to open the floor for any comments.
Something that we always struggle with in these areas, especially when it comes to electricity, you know, is keeping the students interested in it. And that's why I'm always looking for real-world examples and relevant things that I can use to say, hey, you know, your cell phone does this, or your car does this, or you know, something like that I can say, you know, this is why we learn this stuff.
Right. And I think that's a common problem that we all have. I tend to relate a lot of it to motor controls. We do have quite a few motors here on campus, and you know, we put circuits together so that they can actually see a motor turning. If you like lights and bells and whistles, and you know, you can use that or whatever. But it is kind of difficult, and it's a foundation type course. They have to know these concepts to apply them to the nuts and bolts that they get into later on, which, you know, they like that because they can see things move and things happen. But to get there, they have to understand these concepts, and it becomes a problem trying to keep that interest level there. Like I mentioned earlier, we have about a 60% completion rate of those that start to those that complete. And that would be looking across just the sequence of the electrical, which would be a 2-year sequence. Of course, if you go on for the 4-year degree, you're going to be looking at somewhat less than that. But at the 2-year level, the associate degree level, we have about a 60% completion rate of those that start.
Ken, of the students that are coming into your class, do you have a sense for how many of them are coming out of tech prep programs?
We used to keep better track of that than what we do now. You would think it would be the other way around, but I would estimate probably 20% are coming through the tech prep from one source or another.
That's pretty high.
Yeah. We have 2 schools that we work very closely with. And I know one of those schools specifically, every year we get probably 8 to 10 students from them. But I have noticed the last couple of years that our numbers seem to be dropping down because more and more colleges are getting on board with this C-tags and well, originally it was the tags, college to college, and then now the C-tags. So since more of them are getting involved, there's more competition, for lack of a better term, on our part. And so I'm seeing the numbers come down somewhat on that. And I'm speaking from last year because I officially retired this past year. and I'm back this semester just as a temp. So that being said, I'm in the classroom, but I'm not privy to all of the information as far as registration and student advising and so forth. I don't do any of that.
Sure. Thank you.
I think I feel like another challenge that we have too is, you know, we give this class, I teach in a high school, and this would be a junior level class. So the kids have a whole year before they get it. Yeah, exactly. But I think it's very helpful for them to have a background in it, if nothing else, the confidence they get. Just a little bit of familiarity, I think, goes a long way when it comes to sitting down in a college class and seeing it again.
I think probably the biggest difference between college level and your typical high school level is high school level, they can do it as long as you lead them through, you know, step by step by step by step, and they do one thing at a time. But if you ask a question that they have to come up with a sequence of 8 or 10 steps to get to that one answer, they can't do it on their own. And at the college level, you know, coming in the door, we have the same problem, but by the end of the particular course, they have to prove that they can do that. Otherwise, they're not going to be successful with the course. So that's the level that we're trying to get to. And that's the level that your students would have to get to in order to come into the door with the college credit equivalency. Now, how we get there, you know, there's some students that I don't know what you could do to ever get them there. And that's the ones that we, you know, lose by the wayside. Ted, what about at your institution? Any particular problems that you're having?
I'm not so sure he didn't have a microphone.
Oh, okay.
He said earlier he was not on a computer with a microphone.
Okay, that may be the problem. Okay, any other concerns, comments, questions? I was hoping that we would have a little bit bigger audience tonight so that we could get some communication and feedback going. Kind of hard to do when there's only a couple people.
Well, one comment I have is how it's been really eye-opening to me as far as the depth that you go into. You know,
we just lost you.
Can you hear me? Can you hear me now?
Yeah, we can hear you now.
Okay. I don't know what just kicked off. But like I was saying, that it's an eye-opener to me, the depth that you go into at the college level. I think that's a little bit, there's more depth there than I realized.
And that's something that we've observed over the last couple of years with students coming to us from the tech prep programs, that we felt that obviously there was a misunderstanding as to how much depth we were expecting, and that's exactly why we put the rubrics together and the whole idea behind the C-tags, as well as these workshops that we've tried to develop.
As a secondary teacher, do you have any recommendations for us on improving this product as well as follow-up? You know, this is the very first series of these that we've done, and we came into it really kind of blind. and as Ken has just been awesome, an awesome sport and a knowledgeable presenter. Do you have any recommendations for us to improve this?
Well, I would actually, I would like to actually take the class. I mean, I would like to actually be able to sit through it. Unfortunately, that's not possible. But I would like to get, I want to get as much out of the time spent here as possible.
Mm-hmm.
I would, it has been very beneficial, like I say, just to see the depth and to see some of that stuff explained. I'm pretty much self-taught on a lot of this stuff, so it's really good to see that stuff explained in the depth. One thing that that would be great is if we could have like a study packet in advance that had the problems and we could work along with it. I think, for me anyway, that would be very beneficial. I don't know if other people would appreciate that, but
That's a good idea. In terms of the, you said it would be great if you could take the whole course, but obviously there's a number of restrictions. But is that something that we could figure out a way to do that? And if we could do it, how long would it take? How many sessions? Knowing that these teachers wouldn't be coming in as fresh as the students that you normally teach. And what if would there be a way that we could create some kind of a system so that a teacher could get some kind of a certification or credit or something, or maybe build in a benefit to the students that they're coming out of their program? Is that something that we could talk about?
Yeah, I see some benefits there and some possibilities. One possibility that I see, again, depending on the school and the locations. For example, here at Shawnee State, most of the time we have a night session of the course, which a student or a faculty member from a career tech could come in and just audit the course. In other words, they would just sit through the course, but it would tie up one evening a week and for the length of the term. That's one way of doing it, but I think a better way of doing that would be, and again, you'd have to get faculty member that would be willing to do that, is to record the actual class on video, like the IVDL systems that we have, and then you could house that and put that together as a product that they could actually download and view the entire course at their discretion.
Yeah.
And perhaps we could build into that some way that, we could put some type of a assessment on there that they have viewed that, and if that be the case, that they get some type of a certificate or something that would have merit to them at their institution level to help that faculty member to bolster their credentials in some way. That would be beyond my pay grade to figure that part out.